Okay, here we go. So we've said that dy is computed as generically as how have we said that we compute a value of dy? We said it is? Well, that's what it means. How do we compute it? You should be thinking y final minus y initial. Final value of y minus the initial value of y computes how much it changed from its starting value to its ending value. Okay? So, but if y changes along with x, so this course is really about how variables change together. So if y is changing along with x in some relationship, then dy can be determined in a different way. Not by this difference, but by using dx. So when dx changes a little bit, we can compute how much y changes, dy. So we want to talk about that today. A different way of computing dy instead of y final minus y initial. Y final minus y initial is really important. It should make sense. But this is equally important. Okay? So, and this is about, so using dx to determine dy is about the idea of constant rate of change, that x and y are in a constant rate of change relationship. Okay? So let's do an example. You are using your car's cruise control to go 70 miles per hour along a flat, smooth highway. So my question for you, and you should discuss, is how would you explain the meaning of this value, 70 miles per hour, which is the constant rate? What's the meaning of that? Tell the person next to you. So what does that number 70 mean, 70 miles per hour? Talk to the person next to you. Go. All right, so let's hear a few possibilities. Yes, sir. Okay, he said you would travel 70 miles in 1 hour. You would travel 70 miles in 1 hour. Yeah. For every hour that goes by, the car will change 70 miles. Anybody else? Is that basically what you said? Every additional hour means an additional 70 miles traveled. Is that essentially what you said? How many people said something like that? Lots of you, okay? All right, well, this is a very narrow meaning. We want to do much better than this. You know that it means a lot more. You just don't know that you know that it means a lot more than that. Let me show you. Ready? Here we go. It means a lot more than this. What additional distance is traveled in an additional 2 hours? Tell me, how far do you go? How far, if an additional 2 hours goes by, how many additional miles do you travel? 140. So you know something else. What about if you go for 5 hours? What additional miles will you go? So you know more than this. So you know more than the fact that every hour you go. So it's a lot more than every hour you go 70 miles. If you go for 2 hours, you go 140 miles. If you go for 5 hours, you go 350 miles. What about a half an hour? You go 35. See how much you know about this? You know a lot more than this answer. What about in a tenth of an hour? How far do you go? 7 miles. Okay. Okay, so what I'm getting at is this. For any change in time, not just 1 hour, 70 miles an hour doesn't just talk about a change of time of 1 hour. It talks about, for any change in time, what is the change in distance? The change in distance is, what's the change in distance relative to the change in time? What's it? 70. It's 70? Nice, someone said it. 70 times. So your change in miles is 70 times as much as the change in hours. For any change in time, the change in distance is 70 times that change in time. That's a lot broader, stronger statement than just every hour you go 70 miles. Do you see? So we want to change that. We want to change that initial definition to this one. For any change in time, the change in distance is 70 times the change in time. This is really crucial for understanding what that number. So this is our meaning for 70 miles per hour. Or this equation. This equation then gives us our meaning for the constant rate of 70 miles per hour. Again, it's not just that you know how many miles you go in 1 hour. It's that you know how many miles you go in any number of hours. And any change in time, any dx you could pick, to get the change in distance, it's 70 times that change in time. So what about in 10 hours? If I said 10 hours, then dx would be 10, and how many miles would you go? 700. That's a rough trip without stopping, right? Okay? Does it make sense? This is the way we have to think about the meaning of a constant rate of change. That for any change in our independent, the change in the dependent is that constant rate times as much as the change in the independent. Let's try another example. Questions before we go on? Okay, well, again, we're using dx now to determine dy, not y final minus y initial. So you're filling up your gas tank and the gas costs $2 per gallon. What is the meaning of $2 per gallon, the constant rate? Now try it. See if you can do better. Go. What's the meaning of $2 per gallon, the constant rate? Talk to the person next to you. Go. Okay. How about this? Every additional gallon means $2 more in cost. Do we like that? Is that true? That's true. But that's, again, very narrow. So we want to do better. We want to do better than that. All right? So who thinks they can articulate what $2 a gallon for gas means? Oh, you have no, not brave enough. Okay? Yes, sir.
The constant change, or the constant rate of change in price per gallon is 2 times the rate of the constant rate of change in volume of gallons.
You got too many rates. There's only one rate. So we have the rates and then we have the changes.
Oh,
so you were talking about everything as a rate. So go for it.
For the change in price, 2 times the change in rate in gallons for every extra gallon.
For every extra.
Something like that.
Oh, and then you were doing great, and then you went back to 1 gallon. The whole point is it doesn't have to be 1 gallon. Yes, sir. Ma'am, sorry.
For any change in gallons, the change in cost is the rate. It's the rate times the number of gallons.
Okay, for any change in gallons, your change in cost will be twice as much, 2 times your change in gallons. Okay? So what is dx and what is dy? So what is dx? Dx means change in gallons. For any change in number of gallons. Sorry, that ended up too low. Okay? And what is dy? The change in cost. Your change in cost, and we know that now if it's $2 per gallon for any number of change in gallons, change in cost is 2 times that change in the number of gallons. So this is this statement and this equation is about understanding the meaning of the number, the constant rate of change, that 2. This is how we make sense. This equation is how we make sense of the number $2 per gallon. That if you were to put any additional amount of gallons in your gas tank, your cost would go up 2 times that number of gallons. So we're making sense of the number 2 with the equation and with the statement. Anybody have a question? Okay, so I've got some more scenarios. Here we go. A store sells make your own snack mix gifts. So there's a box that costs $B, and then the snack mix costs $2.75 per pound. So I want you to tell the person next to you, what does the $2.75 per pound mean? So when I said which means, I'm just referring to the last part. So the snack mix costs, practice, tell the person next to you, what does the snack mix cost $2.75 per pound mean? Go. It's nothing to do with B. It's nothing to do with B. B is the cost of the box. It has nothing to do with it. Okay, somebody new. What does $2.75 per pound mean? What is the meaning of that? $2.75 per pound means what? Somebody new. Somebody new. Or I'll just pick somebody by the color of your shirt. Yes, sir.
It's like $2.75 per snack mix.
So it's $2.75 for each pound.
Minus the cost.
Minus the cost of the box. I saw you next. Go ahead.
For any change in pounds, the change in cost for snack mix is 2.75 times the cost, the change in pounds.
Well done. Well done. How about in the back? What were we going to say? Same thing. Okay. Yeah. Okay, good. Here it is. Any additional number of pounds of mix will increase the cost by 2.7 times that additional number of pounds. So I just kind of phrased it differently, but that's the point. So given some, if you put more into the box, how much more are you going to pay? 2.7 times as many times the number of pounds that you put in. That's what that means. That's going to increase your cost. Okay, so what I want you to do is define all these variables in the situation. What is x? What is y? What is dx? What is dy? And so these are not one-word answers. It's a phrase that describes completely what x is, including the units. So you want to make no mistake about it. It's going to be a phrase, including units, that specifically defines what each of those is. Go. So what is x, y, dx, dy, and m? Okay. So you're writing out a phrase. You're writing it out. Okay, here we go. What is X? Was that? The number of pounds. The number of pounds, agreed? The number of pounds of mix, agreed. All right, what is Y? No, it's not value. What's it? Okay, it's the cost or the price of a gift with X pounds in it. Okay, so with X pounds in it in dollars. So it's the cost in dollars. Down there. Okay, the cost of the gift that has X pounds in it, and that cost is in dollars. Okay, dx. What does dx mean?
Change in the amount of pounds which will be respect to the price.
The change, dx doesn't have anything to do with price.
Oh.
So it's just the first thing you said. It's just a change in number of pounds. And what is dy? Change in the cost of the gift. Change in the cost of the gift. And so what we're going to call M is the constant rate of change. That 2.75 is what we're going to use for constant rate of change, M. Okay? So write an expression using these variables that computes the change in cost for a change in number of pounds bought. Go. Write an expression using these variables, some or all of them, that computes the change in cost in the number the change in cost for a change in the number of pounds bought. Go. It's actually an equation, okay? That's actually an equation, okay? So if we want to compute the change in cost, what are we computing? We're computing which variable? dy. Change in cost is dy. And so what is the equation that will compute dy? dy is computed how? You said it. What is it? Yes. Was it? Right. Okay, so you could say 2.75 dx or m dx, which is because they're the same. And this equation says exactly what this sentence says up here, which means any additional number of pounds, any dx, will increase the cost, will mean a change in the cost of 2.75 times that change in number of pounds. So this equation right here symbolizes exactly what that sentence says up there. And reflects broadly the meaning of 2.75. Okay? Reflects broadly the meaning of 2.75. Anybody have a question? So everything we do in everything we do every day is important later. So if it's feeling a little easy, great, but let it sink in so you don't forget it, okay? Everything comes around later, okay? All right, after scooping some mix into a box, you decide you want more. The additional cost you pay for 1.5 more pounds of trail mix is 2.75 times $1.5. True statement or not? Agree with that statement? If you scoop 1.5 more pounds in, will you pay 2.75 times 1.5 more? That's exactly what we're talking about. This is exactly so. Define the variables. Go. What are the variables in this situation? What's dx? Oh no. Now I'm asking, what are the values? What are the values of these? What's the value of dx? What's the value of dy? What's the value of them? We've already defined them. We already know what they are. In this scenario, what are the values? dx is what? 1.5 pounds. Doesn't mean that the box has 1.5 pounds of mix in it. No, it does not mean the box has 1.5 pounds in it. It means there was some amount, and what happened? We added 1.5 pounds. It's a change. It's the amount of change. It's not an amount of pounds in the box. Okay? dy equals what? 4.125? 4.125. Is that how much the gift box cost?
No.
Is that how much just the snack mix in the box costs? No. It is how much what? The cost went up. Okay, and I'm making a big deal of this because we've worked with students semester after semester, and it's very common. There's all this confusion between what y is and what dy is, what x is and what dx is. Okay, that's why I'm making a big deal of this. Okay, dy is the amount the cost went up. It's not a cost. What is m? And where did that 4.125 come from? Right, it came from that calculation, which we know is our m dx. And m is 2.75. Question. Okay, next, you remove 0.4 pounds from your bag when no one's looking and return it to the bin. What is what are the values? dx, dy, and m. Go. What's dx? Negative 0.4. What's x? Oh, I got you there. What's x? 1.1. Is it 1.1? 1.5 was a change. 1.5 wasn't the pounds before. It was a change also. What is x? As a value? We don't know. We don't know. It didn't tell us. X is the total amount of pounds currently in the bag, which could change, but we don't know. We know we added 1.5 and took away 0.4, but we never know what we started with, so we don't know. Okay, what's dy? Negative 1.10. Meaning that our cost went down $1.10. It went down. Okay, m is negative 2.75. No, it's still positive. So that constant rate is always positive, so that when we increase the pounds, we increase the cost, and when we decrease the pounds, we decrease the cost. That's a positive rate of change. Okay, that's going to stay positive. Questions on this example? What is y? We don't know. We don't know. Okay. New example. Okay, and after that, I want you to do these variables. So if I'm going to give you y, though. I'm going to give you y. Y is defined as the height of the flag from the ground. The height of the flag from the ground. So 0 going up upward is the height of the flag. Define each variable below completely and precisely. So again, these are, you're defining them with words, so specifically with units. Go. I already told you, y is defined as the height of the flag. Y is the height of the flag. Y is the height of the flag. So x is time is not sufficient. Okay? You need to precisely say what quantity of time are you talking about. Okay? I'm not talking about the unit. Time in seconds is not sufficient. Time in seconds is not sufficient. Okay? What? No, but that would be dx. That would be change in. So we need a good, fully descriptive for x. She said time elapsed in seconds since the flag began to lower. Is there any question in your mind what amount of time she's talking about?
No.
No. And that's exactly right, okay? You have to give that reference point. Time since when? Time starting when, okay? So I said the number of seconds since the flag left the top. So, and that's exactly the same meaning as what she said. She said the number of seconds elapsed since the flag started to lower. But you need to have that reference for the starting time, okay? And we already said that y is the height, okay? So what is dx? What is dx? What's the meaning of that? Somebody knew. Whose mouth is moving? There you are. Okay, go for it. Change in time since the flag left to the top of the pole. And what's the unit on that? Seconds. Good. Okay? So his is better than mine. Yeah, he said the change in time since the flag left the top of the pole. That's better than mine. Okay, change in time in seconds. dy is? Change in height in meters. Okay? And so what is m? Okay, so m is the constant rate of change of the flag's height with respect to the number of seconds since it left. Okay, what's the value of m? Yeah? Sure.
On dx, is it saying it's the change since it left the top? Is that not correct? Can it be a change at any point?
So it's a matter of the way you're hearing that phrase. So yes, you're right. It's the change starting at any time since and ending any time since. So, but both of those times are times since it started lowering. So it's just the way you're hearing the phrase. You're thinking of it perfectly right, though. Okay. What is the value of m? Yeah.
Is it change the height in seconds, time in seconds?
That's right. It's the change in height with respect to an amount of change in seconds. And what is its value? Good. I heard a lot of you say that. You should have picked up that the rate of change here is negative because the height is positive going up, but what's the flag doing? It's going in the opposite direction of positive height. So for every second, the change in height is 0.75, negative 0.75 meters. How about that definition? For every second that goes by, so the meaning of this is every second the height goes down 0.75 meters. How'd I do? Good or bad? At defining that value. Every second that goes by, the height goes down 0.75 meters. True, but narrow, or not a full good definition. So let's go back. What is the meaning of that negative 0.75 meters per second? Somebody knew. Someone totally knew here. Who wants to? Is that him? No. Who wants to say the meaning of the value negative 0.75 meters per second in a A full way, not just the narrow view of what's happening every 1 second. Yeah.
At any change of time, the flag's height decreases 0.65 meters every second.
Oh, you're doing great, but then you said every second. So the whole point is that we know what it does in any change. So you said in any change of time, how much does the height of the flag go down? You almost had it. 0.75. It's not about 1 second. It's about that change in time that you defined at the beginning. Go for it.
For every second interval, the American flag is lowered, it will decrease by 0.75 meters until it reaches 0.
Okay, you still talked about only what's happening every second. So yes, that's true. But we want the broad definition of this value. Yeah.
For any change in time, the change in distance is 0.75 times the change.
Right. For any change in time, a half a second, 2 seconds, 8 seconds, 4 seconds, a tenth of a second. What's the change in distance? Or change in height? Negative 0.75 times that, whatever that change in time was. It's not just about what's happening every 1 second. It's about what's happening in any dx, any change in time. And what is happening in any dx? So what's the expression using these variables that computes the change in height for any change in time? What is it? dy equals negative 0.75. The key here, I could give you any change in time, and you can tell me how much the height decreases by multiplying that change in time by negative 0.75. Not just 1 second and 3/4 of a meter. Any change in time, we can calculate the change in height. Doesn't make sense with that, all right? So what's the meaning of negative 0.75? This equation tells us the meaning. dx doesn't have to be 1 second. Okay, questions on this example? All right, going with that. Go. How much does the height change from 4 seconds to 6.9 seconds since the flag left to the top of the pole? Go, figure it out. And use the symbols. So you're going to answer this question, but not only that, apply all the symbols that we're talking about. X, Y, dx, dy. Okay? And then apply the symbols and solve the question. Okay, I think I'm going to call. Okay, let's see. How about right here? The glasses, yeah. How'd you do? What's dx?
dx is 2.9.
2.9, which came from? Finals minus initial. 6.
dy is 2.75.
And how'd you get that?
I got that line 2.9 times -2.75.
Given any change in time, how do we find the change in height? By multiplying by that constant rate. What'd you get for that? What was the value for dy? What are the units on that? So is the flag below the ground? Is it 2 meters below the ground? Oh, so it's 2.175 meters down from the top? Is that what that means? Careful. So this is the kind of mistakes that students frequently make. Saying, oh, that means that here's the top, so it's down 2.75 from the top.
Those previous equation.
So instead, what does that number mean? The change, right? The change in height from 4 seconds to 6.9 seconds. It's not a value of y. It's how much it changed. M was? Okay. Okay. Questions on this one? Okay, new situation. So before you start writing, listen. I'll read it. Suppose you open your laptop during class, take some notes. Take notes, right? Then, 35 minutes after class started, your laptop battery has a 41% charge. 75 minutes after class started, the battery has a 28% charge. The percentage charge P, or that's going to be our dependent variable, changes at a constant rate with respect to the number of minutes since class began, T, independent variable. So you've got some questions to ask about that scenario, okay? Boom. So do those 4 questions and see how you do. Work together. You're either making progress or you're asking and getting help. Go. Yeah. I have not done that in the past. I just provide the videos. So you can just go through the videos to find the slides. Yeah. Yeah. Because I'm constantly taking my PowerPoints and changing them all the time. So, yeah. Yeah. What are the units of the constant rate? Given our dependent and independent variables, what are the units of the constant rate? What was it? He wants percentage per minute. Okay, so maybe not 6. So just as a rule, don't wear headphones in lecture. I mean, it should be understood. Don't wear headphones in lecture, okay? You can't fully be engaged if you're listening to something, okay? You may think you are, but you're not, okay? So what is the units of M again? Percentage per minute, agree with that? What? No, the loss comes in with our positive and negative, right? So it's just percentage, change in percentage per minute. Okay? What's the meaning of the value? So one last time. Somebody knew. The meaning of the constant rate of change, in this case, if it's percentage per minute. Yep.
It's a percentage of battery loss.
It's the percentage of battery loss per minute. That's the meaning of that value. Corey. Percentage. M. Yeah, good. He said for any change in minutes, the change in percentage will be M times that change in minutes. Good. So M is percent per minute, and its value is the percent change of the battery every minute of time. Okay? Here's my shallow version. All right. The better version is given any change in time, it's the change in percentage is M times that change in time. Okay. What is the value of dt according to the information given? 40 minutes. I told you it went from 35 minutes after class started to 75 minutes after class started. So that's a change of 40 minutes. dt is 40 minutes. Okay, so what would 1/40th represent? Why am I bringing up the fraction 1/40th? What does it represent? Is it M? Is 1/40th have to do with our rate of change, constant rate of change? Nope. Nope. What is it? Right? Yeah, it's talking about what is 1 minute compared to our change in time. 1/40th is what 1 minute is compared to our change in time. So it's the fraction of time that 1 minute is to 40 minutes. In other words, 1 minute is 1/40th of 40 minutes. Okay, what value of dp do we have? What value of dp do we have? According to the information given. Is it 13? Negative 13. Negative 13. dp, final minus initial, negative 13. So here we didn't give you the constant rate, but I gave you all the information about different times and different percentages, so we could use the final minus initial approach, okay? Question on these questions so far? So we have a change in time of 40 minutes and a change in percentage of negative 13%, okay? So, really tune in here. If the battery percent changes negative 13% in 40 minutes, and 1 minute is a 40th of 40 minutes, then how much does the battery percentage change in 1 minute? So we know that 1 minute is a 40th of 40. So how much will the battery percent change? So we're taking 1/40th of 40 minutes to get 1 minute. So what are we going to do to the percent to get how much the percent changes in 1 minute? 1/40th of that also, right? If we're taking 1/40th of 40 for 1 minute, then we're going to take 1/40th of negative 13% to get how much the percent changes in a minute. We're going to take 1/40th of 13%. Which ends up being negative 0.325% per minute. So this may have felt a little weird to you, but what I just did was I just showed you why that constant rate of change is dp divided by dt. Okay? Because we're saying what fraction of 40 is 1 minute. We're going to take that same fraction of negative 13% to get how much the percent changes in 1 minute. And that's essentially negative 13 divided by 40, or 1/40th of negative 13. Okay, so here's our constant rate of change. We know that that means for any change in time, the change in percentage will be negative 0.325 times that change in time. Excuse me. Okay, any questions on what this screen happened on the screen? So now we're getting at the idea that M is dP over dt. And we just kind of reasoned out why M is dP over dt. So up to this point, we were talking all about what? dP equals M dt, which is crucial. But now this little example was explaining how that constant rate of change is the change in percentage divided by the change in time. Okay, so this is like two different faces of constant rate of change. Two different faces of constant rate of change. Any questions? Please.
Regarding the 15 to -13%, would you convert it to 0.8 or 0.13?
No, we can just keep it everything in percent. You don't have to. Yeah, just keep it. It's a lot easier. Just keep it in percent. And so, in fact, that's what we're going to do next. So, in graphing calculator, let's look at this situation in graphing calculator. So, what was the info again? At how many minutes? At 35 minutes, the percentage was 41%. At 75 minutes, so I want to display 2 points that show these two correspondences, right? 35 minutes and a percentage of 41% is a correspondence point. It's the correspondent of two values, simultaneous values of two different variables. I want to graph points that show each point showing these two correspondence points. How do I do it? How do I graph the point that tells me that at 35 minutes the percentage is 41? In GC, what do I do? Control 2. Control 2 plots a single point. Control 2 plots a single point. What is my x value? My y value is? Okay, and now I want to plot the second point. Control 2, 75 and 28. Where are my points? Why aren't there any points up there? Okay, so I've got to have the right scale, right? So I'm up around 35, 40, 75, 28. I'm only showing to 15 on the x, to 6 on the y. So you're learning that you can do them separately, but I need to zoom out on both. So I'll just go ahead and hit the zoom out button. And I can keep hitting it, and there's a pretty decent picture of it, showing my two correspondence points of a time and a corresponding percent, and a time and a corresponding percent. So I want to draw on the graph, say right here, I want to draw from here, I want to draw something that shows a change in time of 10 minutes forward in time. So starting at the red dot, 35 minutes, 41%, I want to draw something that shows a change in time of 10 minutes. What should I draw? What could I draw to represent a dt of 10? So if I'm going to start at this point and do what? I'm going to show a dt of 10. What could I do? What's that? Should I come down here and go to 10? Right here, t equals 10? No, I want to start here and show a change of time. So which direction should I go that would mean a change of time from here? To the right, right? So and if I go to the right, 10. I'm guessing, okay? I'm going to just try to make it a little bit better. Here we go. So there we go. And so that could represent, starting at that time of 35 minutes, that could show a change of time of 10. Would you buy it? Okay. How much did the battery change in those 10 minutes? How much did the battery change in those 10 minutes? What's that? Someone said it. How much did the battery change? The percentage of the battery change in those 10 in that change of 10 minutes? We've been working on it all lecture. dy equals? And how'd you get that? Was it negative 3.125? Is that right? 3.125. Percent per minute. So if I give you a change of time of 10, then the change in percent is 10 times negative 0.325. How can I show that on the graph? So that dy was negative 3.25%. How can I show that on the graph? Go down, right? So I'm going to go down because the percent is up and down. So I'm going to go down. I'm just going to estimate it, something like that. So that would show my dy of negative 3.25%, which came from mdx, right? So now instead of calculating final minus initial, we have a new way. With constant rate of change, you can calculate a change in y by m times, in this case, dt. All right, so one last thing. I left you out early Tuesday, so we'll do just a little bit over. What's the new value of percent? Last question. Don't check out. What's the new value of percent? How do we calculate a new y? We worked on it. Y new equals y old. Oh, you're so much better than last semester. What is y old? What is y old? 41. What was the change in y? Should make sense. It started at 41% in those 10 minutes. It went down 3.25, so you're just going to add 41 plus negative 3.25. So the new percent is? And that's shown right here.